There we go. Yeah, so thank you for the full screen. Thank you for the introduction. My goal with this talk is to keep things reasonably quick and non-technical, partly because this is the last talk of CPP. I'm sure we're all very tired. But also, as Tobias mentioned, this is a project with a lot of authors. I guess I'm advancing this manually. All right. This is a project with a lot of authors that has been going on for a long time, at least 2.5 years, although the roots of this, thanks. The roots of this go back even before that. Mathlib is a project done in the Lean Proof Assistant. Yeah, much better. Yeah, so we have a list of all of the contributors to Mathlib on the screen here. A few of them are in the room. Please chime in if you have anything to add, since this is a community presentation. Right, so Mathlib is a library for Lean. We've heard a few talks about Lean. I'm not going to go into details about the system, except to say, if you're unfamiliar with it, the logic is essentially the same as in Coq. And Mathlib is in Lean 3. So there's a new version of Lean in production that I will mention briefly at the end. Mathlib is for the current version, Lean 3. So library for Lean, Mathlib is a community-driven library for the Lean theorem proving. What I mean by this is that, well, we saw on the last slide, 74 people have contributed. There's no central organization or really aim with the library. What goes into Mathlib is controlled by what these 74 and counting people want to do in Lean. There's no target. There's no big project that is guiding where the library goes. So what is in the library? It's called Mathlib. I say here it's a library of mathematics. This is because of those 74 people. We have a surprising number of people who are interested in formalizing mathematics. And so this is the direction that the library has taken. Now, in order to formalize mathematics, you need other things. For one, you need some sort of automation. You need tools to help make the formalization job easier. And so our tactics are part of Mathlib too. The way that Lean is designed, the language for, for writing automation is essentially the same as the proof language. So we can incorporate the tactics that we write into our library in the same environment. Now, in order to write tactics, we need tools for programming. Since our tactics are written in Lean, we need tools for programming in Lean. So part of Mathlib is designed to support writing these tools. So we have libraries for formalized programming as well, which means that the name Mathlib is maybe not entirely accurate. It represents the majority of the library, but certainly not all of it. So Mathlib is an experiment. It's an experiment in developing a large, single, coherent, sustainable environment for formal math. And I want to emphasize that it's an experiment. I certainly don't think that Mathlib or the Lean system is the final system for doing formal mathematics. I think that there is a ton of progress to be made. There are many other systems out there. We've learned an incredible amount from these other systems as well. I'm certainly not an expert in all of them, but I don't think that any system out there is the final system for formalizing mathematics. I think we're still trying to figure out what we need to be able to have a library like this. And I consider Mathlib another data point in this collection of systems, yet another experiment. And I mentioned, but I want to emphasize, that Mathlib is not designed or developed for any single project by any single group of people. It is, by design, free-flowing in what goes in and where it goes. So a quick timeline of the history here. Lean is developed by Leonardo de Mora at Microsoft Research. The project began sometime in 2013. The current version of Lean was released in early 2017. And that summer, the core library of Lean was separated from the system under the idea that work on the system and work in the library can proceed not completely independently, but they were being pushed by different groups of people. So the core library was separated from the main system. That became Mathlib. Originally, development on Mathlib was led by Mario Carnero and Johannes Hotzel, and others sort of trickled in over the missing year here, over 2018. The crowd of people contributing to this library grew. At some point, it became clear that Johannes and Mario couldn't maintain the project on their own. So about a year ago, we put in a maintainer team of 6 people. And as of a few weeks ago, this has grown to 13 maintainers. We have 74 people who have contributed to the library, and over 200 lines of code in the repository. So the interests of the community are largely, certainly not entirely, but largely mathematical. We have a lot of people from traditional mathematics departments at all levels, from undergraduate to full professor, who have been working on this. The interaction between, well, what I call formalizers, so mathematical formalizers and otherwise, and the people who are writing tooling for the system, who are writing tactics and writing automation, has been a very essential part of the development, I think. The math that's going into the library is informing the tactic tooling that we write, and vice versa. And I think it's also a big goal of the project to be as accessible as possible. I mentioned that a lot of these, well, some of these 74 contributors have been undergraduates. We're trying to bring in people from all kinds of different backgrounds at all levels, especially trying to hook people early if we can. So I'm not going to go into a lot of detail about any particular contents of Mathlib, but here is the high-level summary, the top-level directories of the library. So the data directory is sort of a grab bag of many different things. Primarily data types that are used for programming, but this also contains the development of the real numbers, and the development of the p-adic numbers, various things that have more of a mathematical feeling to them. There's a large library about topology that I'll mention a little bit more of in another slide. The tactic and meta directories contain mostly tooling for the system, so Lean meta programs. But there's a lot of what we can call undergraduate level abstract algebra. In algebra, ring theory, group theory is somewhere over there. There's a model of ZFC in set theory, development of cardinals and ordinals. There's integration, differentiation, and and analysis and measure theory. So this is not nearly as extensive as other libraries out there. My point is just that there's a reasonable amount of mathematics here, and there are some things that, as far as I know, exist only in Mathlib that have not been formalized in other systems. So I'll go into a little more detail on a few parts there, but a few points first. Mathlib is classical in that we make no real attempt to remain constructive. When it's possible to write types that are computable, or write definitions that will compute, we try to do so, but it's not a priority, and there is no attempt made to refrain from using the law of excluded middle. The library is designed around type classes to manage the structure hierarchy, and my next slide will show that off. Lean has computable quotient types. Automation and tactics, as I mentioned, are an essential part of the library, and this is a really core part of the system design. And of course, we've taken lots of inspiration from many other libraries out there. We owe a huge debt of gratitude. So I mentioned that we use type classes to organize the structure hierarchy, And this is just a snapshot of the hierarchy that underlies the definition of a normed field. So there are lots of different type classes here. There are a few somewhat separated portions. You can see a section having to deal with topology and norm structures on the left, and then a more traditional algebraic hierarchy is embedded somewhere in here. We have field, ring, etc. So the idea here is that we can prove lemmas at the appropriate level of generality and use them for any kind of structure that inherits from that type without having to lift lemmas or reprove or restate lemmas in any way. Everything should be handled implicitly by the system. These type classes are generally semi-bundled in that most of them are predicates on a type. The operators that might be part of that type class are bundled into the structure. And so there are known issues that come up. For instance, you can see lots and lots of diamonds in this structure. And in certain cases, having diamonds in your type class hierarchy can lead to some very unfortunate performance problems. And I can't say that we avoid these performance problems entirely. The new upcoming version of Lean will actually have a new type class resolution procedure that will allow us to avoid a lot of these issues. But for the most part, our library is designed in a way that we can step aside from some of these problems. Let's see. So very quickly, I just wanted to mention a few highlights of the library. There's more on this in the paper. The linear algebra corner of the library has actually been used in a handful of other developments. It's been built on top of, which is nice. It's designed as something that can be reused. To indicate how we use type classes, I wanted to point to the definitions of semi-module and submodule. So a semi-module, this describes an R semi-module structure on a type M. So you have to assume as a type class instance that R has a semi-ring structure and that M has an additive commutative monoid structure. We extend another type class here, and we add two fields to this. The definition of a module looks similar. So down here, in the definition of a submodule, we assume that we have module Rm, which gives us access to everything that's been proved about semi-modules and everything that that structure inherits. I thought I had a piece of code down here, apparently not. In the topology section of the library, again, I wanted to mention this because it is a fairly large part of the library. We define some fairly complicated topological structures. We have uniform spaces. We have a notion of the completion of a uniform space. We have topological algebraic structures, so topological groups, rings, normed spaces. This is, as we saw in the type class diagram, in some way it's a second structure hierarchy that interacts with the traditional algebraic hierarchy in many ways. So the Gromov-Hausdorff space with the natural distance, I actually don't know what this is, but I wanted to mention it as one of the highlights, one of the interesting things in our library. So this was defined by a mathematician who had used Isabelle and came across this definition that he wanted to formalize and realized that it's very inherently dependent typed, and he couldn't find a way to work on this in higher order logic, and so turned to dependent type theory instead. And I'm always curious to see examples of this because I know that there are lots of encodings for working with structures that feel dependently typed in higher order logic. But from what I understand, this was nearly impossible to do in that foundation. One more highlight worth mentioning. There's a very general definition of manifold. This is not the general definition of manifold. This is one step toward that. But the definition includes manifolds with boundary, manifolds with corners, and tries to unify this. And there was, again, from what I understand, this is not my area of expertise, there was a good amount of reformulation of known mathematics in order to construct these things. So this is using constructions that are not really written down informally anywhere, as far as I know, as far as the people who formalized it know. The library contains tactics and infrastructure for the system, as I mentioned. We see this as an essential part of the library and not really as part of the core Lean system. So there are some big tactics. The simplifier is actually part of the core system. This is built into Lean. But we have tactics for algebraic normalization, so normalizing in rings and abelian groups. There's a tool that we'll call a tableau prover, plus a few other things, simplifier, et cetera. There's a tool for proving goals in linear arithmetic. But the library also contains much smaller scale tactics that I think are worth mentioning here because they really do integrate into the library. These things are small tools that were designed for very specific classes of problems that use lemmas, that interact with the lemmas in the library in very specific ways. And it's hard to think of these tools as separate from the library itself. They're not something that feels like that should be added in a plugin. They're really part of Mathlib. Also in this note, there are a lot of tools for library maintenance and fine-tuning. So we have tactics that will report their behavior, that will replace themselves with things that are easier to maintain. We have tools for linting, for checking that definitions don't have unused arguments, et cetera. For inspecting an environment. So all of these, again, are part of the library, not part of system development. And having the metaprogramming framework in Lean makes this not only possible, but makes this very pleasant. It really feels like the correct way to do things in our system. So my last couple slides are about the community organization of the project. I mentioned we have 74 contributors, 13 maintainers. This is not a strict hierarchy. So the project is hosted on GitHub, and we encourage anybody to comment on, to review pull requests. The maintainers have the final say over what gets merged, but it's supposed to be a discussion among everybody involved. And there is very frequent discussion and collaboration on the Zulip chat room. Everybody is welcome to visit. We don't only discuss Lean. But this is really, I think this has been a big reason why Lean has accumulated a group of mathematicians who are interested in using it. There's this chat room where they can show up and ask whatever questions they want, and people who speak the same mathematical language as they do are there and willing to hang out and chat. I think Johan said something similar in his talk. Yeah, so a couple closing notes. I think yes, I should close now. There are questions, of course, about the scalability of the system and about the scalability of this community model. I don't have deep answers to these. In many ways, I feel that Lean 3 has scaled very well. There are we're approaching the limit of what we can do with the current type class system, and Lean 4 provides the answer to that. So Lean 4 offers many new features. The downside is that it will not be backward compatible. So in the medium term, there will be some sort of porting process to move Mathlib to Lean 4. The details here remain to be seen. Unfortunately, I don't have much more to say about that, but we hope that it won't be horribly painful. So I will end on that note, with a downer note. Thank you very much.
We have time for about -1 question.
One question about Lean 4. When you expect to be released? Because I follow some discussions, and it's in some indefinite future. Will it be in a year or 2 years or 5 years?
So Lean 4 is public. It's on GitHub. You can download it. You can build it. As far as I know, it's a pre-release. I mean, there's no official release at the moment, and it's changing very fast. I'm not a system developer. I can offer no promises on their behalf as to when it might be finished. But it is available now.
Last question?
Two somehow related questions, which is about coding style. Do you have a way to instruct contributors about coding style that is preferred for the library? And the other about documentation. Do you build documentation together with the code, or there is nothing established for now?
Yes. So as for coding style, we have guidelines on the GitHub repository. We have many community members who are happy to jump on a pull request, and even if they don't want to correct the formalization, they're happy to make comments about coding style. As far as documentation goes, so this summer we put in new... sorry, I need to just find this page here. Over the summer, we put in new guidelines for documentation and have fairly recently started generating HTML documentation. So I can move this so I don't stand in front of the screen too much, or not. If, for instance, you are curious about manifolds, where are manifolds? Geometry, manifolds. You can go read about manifolds, how they're implemented, see all of the definitions about manifolds. This is all hosted now on the Lean Prover community website. Of course, the entire library is not documented yet, but we are working on it. New things are documented.
Right, and I think with this we've come to the close, and I think we shouldn't just thank the speakers of this session, but we should thank especially the organizers, the PC Chess, Katalin and Jasmin,